for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching. Hi there.
Welcome to School Not Out, your daily classroom for CSEC and CAPE students. You can watch this lesson real time on Television Jamaica's YouTube channel or One Spot Media. We're also live on Music 99 and GoJamaica.com. If you have any questions on today's subject, you can send them into Television Jamaica's Facebook page or Instagram at television_Jamaica. Today's lesson is on CSEC physics. We're going to focus on heat and temperature. I am Pethorn Dawkins. Alright, good morning again, students. Welcome back. Last week we were looking at the intricacies of current, electricity, Ohm's law, that type of thing. I decided to jump a little bit closer to food form work in terms of the material. And I've decided to go and look at things that you should already be familiar with, heat and temperature. Now, these kind of things are everyday experiences. You feel hot, you feel cold, you go into an AC room, you go into a sauna, you feel the heat absorbed by your body, you feel your body getting cold, shivers, all of that. We're going to delve a bit deeper into what this whole thing is, heat and temperature. I'm going to look now at how heat affects materials and how temperature really is measured and all that type of thing. Alright, so if you want to follow, you can check back in the latter part of fourth form going into fifth form work when you was looking at thermal physics, you know, that type of thing, expansion, gas laws, that type of thing. Alright, so heat and temperature. Let us get into it. What is heat? It is that form of energy, and sometimes they refer to heat as being thermal energy. Two terms are interchangeable, which is associated with the random motion of the particles that make up matter. From 8th grade science, you would have already known that matter is composed of tiny, hard to see or near invisible particles. And these particles, they say, are in constant random motion, the kinetic theory of particles. So when it comes down to heat, heat now is that form of energy that affects the vibration of the particles. The greater the amount of thermal energy or heat that any particle of matter possesses, the faster they will move, the more vigorously they vibrate, and the harder they will collide with each other. So pretty much when you look at how heat affects particles, you must understand that the particles that are in random motion, constant random motion, when they add heat to it, they will vibrate more vigorously, they will move faster from place to place, and of course when they collide, because they are bundled together, they will collide harder and more frequent with each other. What is heat again? It can flow through matter, materials, by transmitting vibration and or electromagnetic energy, big word, from a high energy region to a neighboring low energy region. So when heat flows, it does so through material most times, but it doesn't necessarily need a material as we look at. But just know that pretty much when heat is flowing, it is flowing from where there is a lot of heat or high temperature region or high quantity of heat region to where there is little or none. That is how heat behaves. Alright? And of course, being energy, it is measured in the unit of joules. From mechanics in the first part of fourth form, you would have been familiar with the unit of energy when you were looking at energy conservation and that type of thing. What is temperature? It is a measure of the absolute amount of heat or thermal energy that an object possesses. So heat is that energy that particles possess. Temperature measures the amount of heat that an object has. Higher temperature objects have more heat, naturally, and of course lower temperature objects have less heat. A temperature difference drives a heat flow process. So when things warm up or when things cool down, what you should understand is that heat is flowing from a region where there is a lot of heat to it and it warms up if it's cooler, or if it is hot and it is next to something that is cooler, heat will flow from it. So a temperature difference drives a heat flow process. The greater the temperature difference, the greater the flow of heat between two regions. So as it is right now, I'm in studio, place is a bit cold, my hands are cramping up. Why? Because the air surrounding my hands is cold. My hands being attached to me, body temperature is warm. So heat will leave my hands to the surrounding air and I will feel the sensation of colder For you feeling warm, it's the opposite effect. Somewhere around you or next to you is warmer than you are. So heat will flow from it to you. The greater the temperature difference, the greater the flow of heat, quicker you warm up, quicker you you cool down. What is temperature? Heat always flows naturally from a high temperature region to a low temperature region. To achieve the opposite, external work must be applied. So what this means is that if you put a bottle of water inside of a freezer, you realize that eventually it turns ice. You would have associated ice with coldness. So what happens is that the region inside of the freezer is colder than the water that you put in. So heat will flow from the hot container to the colder region inside the freezer. The opposite effect takes place when you put something in an oven. An oven is much hotter than whatever you put in it before you start to bake or cook or whatnot. So the oven, being a high temperature region, will supply heat to whatever goes in, which is of a low temperature region. So heat always flows from high temperature to low temperature. But you don't necessarily always will have that in every situation. For example, as I said, in this room it is cold. But naturally objects want to warm up because outside is warmer. So what's happening there? What needs to happen for that to take place is that some external work needs to be put in. So that is why you have to pay electricity bill for air conditioning. That is why AC in cars, they need the engine to be running. Some work, some external work must be done for you to have the opposite, which is heat flowing from a colder region to a warmer region taking place. All right? It doesn't naturally happen in nature. Heat flows from high temperature to low naturally. For you to reverse that, you need work. Absolute temperature, and we'll talk about that in a bit, is measured in the unit of Kelvin, and the symbol for that is capital K, not common K, capital K. The other are relative units are degrees Celsius and degrees Fahrenheit. Now, what do I mean by absolute temperature? Typically, when you quote Celsius or Fahrenheit figures, you can quote a zero figure and you can quote a negative figure. Since temperature is a measure of heat, a negative reading or a negative value of temperature would indicate that you can have negative heat. That is not possible. So what happens is that you have to have a scale of measurement that deals with the absolute value of heat. That absolute scale is a Kelvin scale. So at 0 Kelvin, which is theoretical, nobody has ever really attained it. They've approached it but never really attained it. At 0 Kelvin, there's absolutely no heat whatsoever. But for typical scales, degrees Celsius and degrees Fahrenheit, 0 degrees Celsius and 0 degrees Fahrenheit, you still have some level of heat. How do you know? Because you can go below that. There's a negative of Celsius and Fahrenheit. So these are relative scales. But in science, in physics, we like to deal with absolution, so we deal with the Kelvin more often. But don't worry, Kelvin and the Fahrenheit and the Celsius can be used. And there's a conversion that can be done to interconvert between the two. Now, where can heat be found? 3 examples are given here. The sun, of course, which is the main source of heat. Fire, light bulbs and stoves. When you light a fire, when you light a stove, it feels warm. When you turn on light bulbs, more or less, well, with the LEDs now, they're a little bit cooler. But like with the incandescent, the filament bulbs, those are extremely hot. Yeah, they give off heat. And rubbing 2 objects together, of course, a closed iron gives off heat as well. And rubbing 2 objects together, when you want to warm your hands up, you just rub them together. You feel them getting warm. Friction. Friction can also generate heat. How do we measure heat? Heat energy can be measured using devices that are designed to produce a physical change when they detect a temperature change. So any temperature measuring device must have the ability to change in response to a temperature change. So when something is getting cooler, something must change for the device to operate. When it's getting warmer, the change must be the opposite. Alright? So once you are able to achieve this, then it can now become a temperature measuring device. And there are different devices that can be used to measure temperature. Thermometers, which most persons, if not all persons, are familiar with. Thermistors, we get to what that is. And thermocouples. For those who do physics, thermistors and thermocouples, you know what this is. For those who don't, you may learn a thing. Stay tuned. Thermometers. This device reports a change in temperature by allowing a contained fluid to change in volume. Now, changing in volume means that you either get bigger, expand, or contract. And it is a contained fluid, meaning that it's a contained liquid or a contained gas. Has to be sealed, and when you apply heat or when you allow heat to flow to it or from it, then it either expands or contracts respectively. And there are different types or categories of thermometers. There are 4 listed here: mercury in glass thermometer, alcohol in glass thermometer, clinical thermometer, and of course the constant volume thermometer. The first 2 you're more familiar with. The clinical thermometer, persons who work in medical or health services will be familiar with. The constant volume now are for the scientists. That's the least popular. This is a diagram of the mercury in glass thermometer. The bulb is there, shows the stem where the mercury travels through. The markings, the numbers on there are basically graduated markings for temperature values. So a thermometer will have markings. A thermometer will have a point where it touches the region that you're measuring, and then it will have a point or a section where the liquid is allowed to expand. Here we have an alcohol in glass thermometer. Now the difference between the two is simply their names. One is mercury, one is alcohol, but their construct is basically the same. Alcohol is colored liquid, mercury is silver liquid. For the clinical thermometer, it is a mercury in glass thermometer, but really and truly what is happening is that it has a much narrower range for temperature readings. The range is typically between 34-35 degrees Celsius to as far up as 42 degrees Celsius. It's a very narrow range, and the reason for that is because it measures body temperature. Your body temperature should not fall below or go above a certain range. If it goes below, that's a problem. If it goes above, it's a problem. So typically, it doesn't really need to read below or above that. Below or above that, you're clinically considered to be in trouble or near dead. Alright, so just think of the mercury in glass, but a much narrower range. And of course, the constant volume thermometer is a thermometer. To make it simple, you allow a gas to expand. The gas pushes down on mercury, and then you adjust it now to balance it back out. So it was at a certain point, the gas expands, pushes it down, and then you move this point now to bring it back up to the level where it was. And then based off this difference here, it is able to calculate the temperature. You don't need to know it for CSEC exams per se, but this is something that you should be familiar with if you go further on into physics. Thermistor. Now, thermistor is a combination of 2 words, thermal, resistor, thermistor. This device is able to change its electrical resistance when it detects a change in temperature. To operate, it needs a power source to provide a voltage across its terminal. The best example of a thermistor working is the temperature sensor in a motor vehicle. That dial or gauge or indicator that's inside the vehicle, they work off thermistors. Since the vehicle electronics and the dashboard is powered by electricity, to get a reading, they send power to a thermistor. Based off the resistance, remember Ohm's law, voltage, resistance, current, right? What happens is that when the temperature changes, the resistance will change, and based off that change, they can now calibrate it, set it up to read off the temperature that you want to read off. Typically, it's a narrow range, so it's not a major thing, and they don't really need numbers, because you don't really see numbers for temperature inside of a vehicle. It's just a gauge. But just know that a thermistor operates like that. And there are other thermistors, circuit boards, electrical devices used at homes. Just know that thermistor is thermal resistor. And our thermocouple. This device is able to generate an EMF or voltage across 2 dissimilar, meaning that they're not the same, metals that are joined together at a junction when the same temperature difference is created along the lengths of both metals simultaneously. Quite a mouthful. Let me just break it down for you. Here is one metal, here is another metal. They're not the same. They're joined together at a point, and that point is what is used to measure that temperature. The other ends now are kept at the same temperature. So basically, between this wire here to here and this wire here to here, are the same temperature differences. However, what happens is that there is a voltage that's created here and a voltage that's created here due to these temperature differences. But because they're not the same, the voltage differences between this one and that one will be different. So once you put a meter on the both ends, you'll get a difference in voltage, and then based off that you can now know what the temperature is. As I said, these things you just need to be aware of. If you go to K physics, then you go a little bit deeper as to find out how this ticks. You just need to be aware of it now, so that's why it is there. Heat transfer mechanisms. Now, heat can be transferred from one region to another by three flow mechanisms: conduction, convection, radiation. And we're going to look at each of the three in a little bit detail, but just pay attention to the diagram here. All three are illustrated here, and for persons who have been near a fire, have put something inside of a fire, if it's a metal, you'll know that the metal gets warm. If you put your hand over the flame, you feel heat. When you put your hand near to it or even stand close to a large fire, you'll feel the heat. Now, thermal conduction. This mechanism involves the flow of heat by transmitting vibrational energy. Remember kinetic theory? Right. By transmitting vibrational energy from one high energy particle to another that's adjacent or next to it. This mode requires a physical medium to travel. It cannot travel in a vacuum. So here we have, I think this is a wire, right? We have a heat source, heat in one end. The particles at that point will start to vibrate vigorously because you're adding heat. The particles next to it, they don't get that benefit because the heat source is not there. But if they wait their turn, you'll find that they get the energy as well. Why? Because sharing is caring. The particles that get the heat, they give it away. So the particles next to it, they get some. The particles next to those, they get some. So eventually, the heat energy that is here moves all the way to the other end, and the entire material now will eventually reach the same temperature. That is how materials warm up and convert or transfer energy by way of conduction. So the next time you put a metal fork or knife or whatever inside of a flame and eventually the handle gets hot, it's because the particles was giving the energy over to each other. Everybody got to the same temperature. Convection. This mechanism involves a transfer of heat energy by way of mass flow of a fluid, liquid or gas. So liquid or gas is termed collectively as a fluid, and this occurs only in a liquid or gas, as we'll explain. The heated portion of the fluid becomes lighter. This means it becomes less dense. So remember density, mass over volume, right? So if you heat something, it will naturally expand. Particles start to move away more. When the volume increases, the density will decrease. So when you heat something, it expands, it becomes less dense or lighter, quote unquote. And that causes the liquid now to rise. The colder portion of the same fluid, which is heavier, quote unquote, or more dense, replaces the heated portion. So the diagram here shows what is happening. You heat it at the bottom of it. One portion gets hot, starts to rise. The colder portions that are on the outside or the periphery of the container, they are colder and they sink. So we have rising of hot fluid, sinking of cold fluid, and that sets up now what we call a convection current. It's a similar thing what happens to wind on the earth. The equator is the hottest part of the earth. The poles are the coldest part. Polar ice caps, right? So what you find is that the equator is heated, the poles are not so much heated. Air surrounds the entire globe. So the heated air starts to move towards the colder regions. The colder regions now not wanting to have a vacuum, because if air moves away, you're going to create a vacuum. So the colder air now is going to replace that hot air that moves. So wind currents are actually as a result of uneven heating of the Earth's surface. Alright? So the convection currents can occur in air, it can occur in water. So anytime I've probably seen this before. If you're heating water, you see like some streaks moving inside the fluid. It is because of mass flow. Mass flow simply means the water as a lump of mass moves. It's not one particle, but a lump of the water moves with the heat energy. Alright? So that's what happens with convection. On to radiation. This mechanism involves the transmission of heat energy via electromagnetic radiation. Electromagnetic radiation is just simply that form of energy that is composed of oscillating particles, that type of thing. When you start doing waves and optics, we delve a bit deeper into that. But just know that heat can travel by way of electromagnetic radiation, and that is emitted or absorbed by objects. Objects typically absorb radiation and they emit radiation, and the form in which they emit it is heat. Infrared, right, your body gives off infrared radiation. That's thermal radiation taking place. This mode can occur in a vacuum and it takes place at all temperatures. So heat gets to us from the sun. Remember, the sun is the ultimate source of energy. Heat gets to us through a vacuum. There's nothing in outer space, as they say. Alright, so there's a vacuum, but that doesn't stop the heat from getting to us. That doesn't stop us from really feeling hot and sometimes feel like we're burning up. Reason for that? Energy can transfer via radiation from the sun to us. Alright, and that's by radiation. So we have looked at all three modes of heat transfer: conduction, convection, and radiation. Now, we're going to look at the effects of heat on matter. Adding heat or removing heat from matter will cause one of two of the following. Either a change in temperature of the material or a change in state or phase of the material. Remember, temperature is measure of hot or cold? Right. But here's a new thing: change of phase or state. From as far as grade 7 science, you should be familiar with the 3 states of matter. From what I'm hearing nowadays in the scientific world, there are about as many as 5 states. But we're not going to get into that. Just know that there are 3 states of matter that you should be familiar with: solid, liquid, and gas. So, for us to change phase, change state, you need to add or remove heat. Alright? Yes. So you need to add or remove heat. So what is happening here is that once you add or remove the heat, you either change in temperature or you change in the phase of the material. The process that occurs depends on the initial temperature of the material. So if you're starting with ice, you may or may not have a temperature change. If you're starting with water at room temperature, you definitely have a temperature change. If you're starting with steam, you may or may not have a temperature change. It depends on the initial temperature of the material. But just know it's either change in temp or change of phase. Now, best way to illustrate this of heat addition or removal on a material is the heating or cooling curve. Persons of chemistry, you would have heard this before. So here we have a heating curve, and we have next a cooling curve. So let me just explain this heating curve a bit. This shows what typically happens for pure water. If you look at the temperature axis, the vertical, we have -40, -20, 0, 20, all the way up to as far as 140. Now, this is a typical shape for pure substance. What do I mean by this? If you're starting with the solid would first increase in temperature because it's all solid. But when it gets to a special point of temperature, it stops increasing temperature. That which starts to happen now is called a melting process. Simply, particles of the solid start to move further and further apart until they now become a liquid. So we have temperature increase, hits the melting point, temperature remains constant even though you're adding heat. When it's all now solid becomes liquid, can't do any more conversion, so what? The temperature starts changing again. When it hits the boiling point, guess what? Temperature stops increasing again. Heat is still being added in now, but what we have now is a different process taking place. So it stays constant for a time, and that is because liquid now is converting to gas. When all the liquid has become gas, no more conversion, therefore the temperature starts to increase. Alright? So that is the heating curve. Solid, flat lines melting, liquid, flat lines for boiling, gas, and then it continues like that. The cooling curve is exactly the opposite of the heating curve. You start out with the gas cools, it hits the melting, the condensation point, The opposite of boiling is condensation. So we hit the condensation point, the gas becomes liquid. When all the gas becomes liquid, liquid cools. We hit the point where the liquid now wants to become a solid. That's what? Freezing? Yes. So we have a freezing now, liquid becoming solid, and then all the liquid becomes a solid. Then of course, naturally, heat will start to be released and the temperature will fall. So heating curve, go up, flat line, go up, flat line, go up. Cooling curve, go down, flat line, go down, flat line, go down. And this is typical for any pure substance. Alright? Now, let us look now at heat capacity versus specific heat capacity. For section of both graphs that show a change in temperature as heat is transferred, sections of slope. So these portions, the gas, the liquid, the solid, these are portions of slope. Alright? So we're dealing with temperature change there. So for section of both graphs that show a change in temperature as heat energy is transferred, this represents a unique property of all pure substances. It's heat capacity. What is heat capacity? It is defined as the total amount of heat transferred to or from a material that produces a 1 Kelvin temperature change of the material. So to explain, we consider this marker, and this marker is at a certain temperature. Say, I believe the room is about, say, 20 degrees or less, but let's say it's at 20 degrees. And then you add a specific amount of energy, and when you add that special amount of energy, it increases to 21, then you can know what heat capacity it has. Because heat capacity, as the name suggests, is the ability to store the heat without you changing the temperature. Alright? So the greater amount of heat that it can store without changing the temperature, then the greater its heat capacity value. Alright? If you have any questions on what we have done so far, you can send them in our various platforms, and I will see if I can answer in the final segment. When we come back, we answer your questions and wrap up. Stay with us.
COVID-19 tip. Protect yourself and others from getting sick by washing your hands after coughing or sneezing, when caring for the sick, before, during, and after you prepare food, before eating, after toilet use, when hands are visibly dirty, and after handling animals or animal waste.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing with a tissue and dispose of it. Avoid close contact with anyone with a cold or flu-like symptoms. If you become ill, please visit your doctor or the nearest health center and share your travel history. The flu and coronavirus can kill. Let's protect each other. A message from the Ministry of Health and Wellness.
The Ministry of Education, Youth and Information, along with TVJ, present Schools Not Out, CSEC and CAPE lessons live Mondays to Fridays from 9 a.m. to 12 noon, with weekly Schools Not Out tutorial sessions on Saturdays from 1 p.m. to 4 p.m. Schools Not Out, live CSEC and CAPE lessons here on TVJ.
COVID-19 tip. Protect yourself and others from getting sick by washing your hands after coughing or sneezing, when caring for the sick, before, during, and after you prepare food, before eating, after toilet use, when hands are visibly dirty, and after handling animals or animal waste.
Reduce your risk of viral illnesses like the flu and coronavirus. Wash your hands frequently with soap and water. Cover your nose and mouth when coughing with a tissue and dispose of it. Avoid close contact with anyone with a cold or flu-like symptoms. If you become ill, please visit your doctor or the nearest health center and share your travel history. The flu and coronavirus can kill. Let's protect each other. A message from the Ministry of Health and Wellness.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching.
Welcome back to Schools Not Out, your daily classroom for CSEC and CAPE subjects. Today we have been discussing CSEC physics, heat and temperature. Alright, so before the break we were looking at this slide. For sections of both graphs we went through that unique properties, heat capacity, and we were talking about what heat capacity was all about, which is really the ability of a material to store heat energy without its temperature changing. If its temperature changes, then you know what heat capacity it has. Alright, and the greater the number, the better the heat capacity of that material, and that may mean something for the material in terms of its being used, its use as a thermal conductor, insulator, and that type of thing. Now, when you're dealing with definite amounts of the material, for example, a kilogram, 10 kilograms, 1,000 kilograms, etc., then the specific heat capacity of that substance must be defined in terms of the precise value of heat involved. So here's the thing. Before, we only looked at the marker and said that, well, alright, the marker is at 20 degrees Celsius. We add, say, 400 joules, it goes up to 30, up to 21. If you add a 400 joules, it goes up to 22, so on and so forth. So every 400 joules changes the temperature by, say, a degree Celsius or a degree by a Kelvin. But in terms of the specific amount, say for example, now you wanted to find out now, alright, if this is a kilogram or half a kilogram, how much heat is required for that half or 1 kilogram? If you find out for 1 or half kilogram, let's just agree with 1 kilogram because that's easier. If you know how much heat is required for 1 kilogram, say you scale this up now to say 5 kilograms. If you scale this marker up to say a 5 kilogram marker and it's the same material, then you would know that, well, if 1 kilogram took 400 joules, then 5 kilogram must naturally take 5 times the 400 joules, which is 2,000 joules. Alright? So when you're looking at the specific amount of the material, then you're now looking at specific heat capacity. So the difference between the two is that one now just looks generally at the material, the other looks at a specific amount of the material, which is of course the mass, and it is typically taken as 1 kilogram. So the definition: specific heat capacity is defined as that value of heat transferred to or from, because remember heat flows either way, a 1 kilogram mass of a pure substance that will produce a 1 Kelvin temperature change. So before heat capacity, just looked at the amount of heat for 1 Kelvin. Now, specific heat capacity looks at that amount of heat for a kilogram, has to be the kilogram, per degree Celsius or per Kelvin temperature change. Equation time. Now, here we have just a bunch of things happening here. Let me just kind of break it down for you. Remember that magic triangle that we looked at some time ago? Yeah? Where we have two things, two things that combine to give a third? Well, the magic triangle can extend to 4 things. Before it was 3. Remember Ohm's law, V equal IR? Right. Here we have now energy, mass, specific heat capacity, and temperature change. So the triangle, that magic triangle, is actually shown here. At the top you have energy, we have mass here, temperature change here, specific heat capacity. Or sometimes they call it E is equal to MC delta T. Alright, let me just write that here. E is equal to MC delta T. Some books may use MC Q is equal to MC delta theta. It's the same thing. Some persons use delta theta, some use delta T, some use Q for heat, some use E for heat. It doesn't matter. Just know that the symbols represent what they do in the equation here. So M is equal to delta E, change of heat, C times delta theta, which is the same thing as delta T. Delta theta or delta T is E over C times M. C is equal to E over C times delta T or delta theta. Alright, and you can see the hand covered there. Now over here shows the equation for heat capacity, which only considers Q or E, energy, and the temperature change. Remember, energy, temperature change. Here we now look at the heat, the mass, and the temperature change for specific heat capacity. Alright? Now, some information on it, significance of it. The greater the specific heat capacity of a material, the more heat needed to transfer, absorb, or release per kilogram to produce a degree Celsius or temperature, a degree Celsius or a Kelvin temperature change. Alright? Materials with higher heat capacity values store heat better and undergo smaller temperature change than materials with lower specific capacities. What this means is that the higher the value of heat capacity for a material, the better it is able to store heat and the less liable or the less likely it is for its temperature to change. It comes into play when you're dealing with water and metals. We look at that. Good heat conductors typically have lower heat capacity values, and poor heat conductors or insulators have higher heat capacity values. And it stands to reason. If you want to insulate something, you don't want your temperature to change a lot when you absorb heat. So if you want to insulate, you want a high specific heat capacity. If you want to conduct, you want your specific capacity to be low because your temperature changes quickly. Here we have some typical values, and we talked about the metal and the water. Aluminum is 900. Oh, and the reason why you see two columns here is because of different units. Column on your left is joule per kilogram per degree Celsius. Column on your right is joule per gram per degree Celsius. So because of the different kilogram gram here, the numbers differ by 1,000. So 900 divided by 1,000 is 0.9. 380, 0.38, so on and so forth. So it's the same value. But let's just look at, say, a typical metal aluminum and say a typical liquid water. Now you see that these values are much different. Water as a natural substance has the highest heat capacity known to man. And that comes into play as significant and important when it comes on to things that live in water. Water doesn't warm up easily, but when it gets warm, it doesn't cool down easily either. Metals, on the other hand, because of their heat capacity values being so small, the minute you apply heat to it, temperature shoots up. So you realize that metals now will conduct heat much quicker or better than water. And these are those typical values shown there. Alright, a quick question. The second group of students determine the specific capacity of a liquid. One set of results is described below. It takes 300 seconds for the temperature of 0.1 kilogram of the liquid to be elevated from 25 degrees Celsius to 50 degrees Celsius. Energy supplied was 13.6 kilojoules during this period. Assume no heat was lost and ignore the heat capacity of the container, so only looking at the water, determine the value of the specific capacity of that liquid. So, we have a situation where we know the heat, which was 13.6 kilojoules, which of course converted is 13,600 joules. We know the mass of the liquid, which is 0.1 kilograms. We know the temperature change, because the temperature change is the temperature final minus the temperature initial, which the final temperature is 50 degrees Celsius. Initial temperature is 25. So that is 25 degrees Celsius change. And we're asked to find C. Now from the equation that was given to you earlier, I'm just going to use my own symbols. You can use like this. M, C, delta T is there, and E is there. So to find C, it is E over M times delta T, which is of course the 13,600 over the 0.1 times the 25, and that is 13,600 over 2.5, which gives 5440 joules. And the units now. This is joules, that's kilogram. Let me write it in different color marker. That's joules, that's kilogram, that's degrees Celsius. So the units here are joules over kilogram, and you can say degrees Celsius. Or the other way to write it is joule per kilogram per degrees Celsius. Alright, so that is your value for your specific heat capacity. It's 6 marks. It's a quick and easy 6 marks question that you can get. You just need to write out the values given to you. This gives you a mark to work that out. This gives you a mark to convert. Stating the equation gives you a mark. Doing the math, stating the correct units gives you a mark. It's easy to strike marks on this. Alright? For specific latent heat now. Specific latent heat deals with the phase change part of the process. For sections where there is no temperature change, this represents a phase change. During that phase change, we have heat energy adding or taking away, but it does not change the temperature. What it does, it changes the particle arrangement. Particles that are doing like this, they start moving faster and faster and faster. So a solid that was locked together starts to pull apart, become a liquid. Liquid that is close together but not as far apart as gas, they start moving apart. So the heat added during latent heat actually goes to change a phase. Solid becomes liquid, liquid becomes gas. No temperature change will take place during a phase change process. Alright? The change in energy results in the particles dominating intermolecular forces. So the particles will start pulling apart because of the heat energy being added. Or they will start to come together because they're losing heat energy. Specific latent heat is this precise heat value added or removed per kilogram of the substance as it changes phase. Alright? And that's the equation for it. Similar to the one that we have here, it's just that now we're looking at L instead of M. And the units are given there. And there are 2 types of latent heat. There's fusion for boiling, for melting and freezing, and then there's vaporization for boiling and condensation. That's all for today for CSEC Physics, heat and temperature. I hope you grasp most of the points we discussed. You can catch a repeat of today's lesson on JNN Today at 4 p.m. in Schools Not Out highlights on Saturday between 1 and 4 p.m. right here on TVJ. It will also be on video demand on One Spot Media. Until next time, I'm Petron Dawkins. CSEC English A is up next. Take care.
Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here. To see our full videos on onespotmedia.com, click here. Thank you very much for watching. Hi there, I'm Simon Preston from TVJ. Thank you very much for watching our YouTube channel. To see our latest videos and also to see live events, click here.